Today we're looking at differentiating trigonometric functions. Now we're not going to look at the formal proof. Two reasons. One is the proof itself is not required in the advanced course, but the second reason, even if I was to go through it and just show it to you out of interest, it contains a couple of bits of algebra in the trig that we're not going to see in this course either. So rather than just look through it and say, oh, okay, I'll have to trust you, to me it makes a lot more sense to look at what I would call an informal proof or an informal proof of why these trigonometric functions differentiate the way they do. Now again, this is not a formal proof, but it should make a lot of sense. We should almost be able to guess what the differentiation of this graph, y equals sin x, looks like. And let's have a go at doing that. Now, we know the key points of this graph. Every 90 degrees, or pi on 2, it goes through a point of interest. By a point of interest, I mean the origin, its high point of 1, the origin, its low point of 1, and continues on and on in both directions. We've already seen what the gradient of this function is right here at the origin. In our last lesson, we considered what happens when we take the limit as x approaches 0 of the gradient here. Now, gradient is rise over run, and we said if we zoom right in, then what we have on this function here, if we're graphing y equals sine of x, the y value, well, that's just the sine of x, and the x value, that's x itself. So when we build the gradient and consider sine x over x, we found that the gradient is actually 1. And that made a lot of sense because it was sandwiched in between two things that had to also be 1, remember? So if we know this, then we've got our gradient here of 1, and we can reason it will be 1 every 360 degrees when it passes through those equivalent points. We can also look at the gradient in lots of other places. I can see that the gradient right here is 0 because this is a maximum turning point. So if I go ahead and just write the gradient here and here where it's 0, and then think about the gradient in other places, I know this is 1, and over here it will be 1. Now if I can just consider whether it would be positive or negative, well, this is a positive gradient all the way up here. So let's just put a series of little plus signs. Then we've got a negative gradient all the way down here till it's 0 again, and then a positive gradient again. All right, now there's symmetry on this curve all over the place, isn't there? So this angle here, if it's got a gradient of 1, what do you think the gradient of this might be? Well, it's same, but flipped over and opposite, isn't it? So this would be minus 1. All right, let's start graphing what we know. If we're graphing the gradient function, then on the y-axis, we'll put dy dx. And on the x-axis, we'll have those same points of interest. Our gradient at pi on 2 is 0, and it's 0 again here. Our gradient is 1 here, so let's make that 1, and minus 1 here. So if we have, a little bit higher, let's have minus 1 there, then at this point it's minus 1. And here again it's 1. Now, how does it get between these points? Do you think it might go down like a V shape and then back up again like a V shape and then down? Probably not. Let's look at the shape. From here at 0, it would just become a very, very slight fractional, like a fractional negative, like maybe minus 1/10 or something. You know, then it would be slightly bigger, maybe minus a quarter, minus a half, until eventually it gets down here to minus 1. It's changing gradually, isn't it? And the curve in this gradual nature of the change is echoed down here. And what we get is the exact same shaped graph as the graph itself. But it's moved along and it's in a different location. Now, that's going up a little bit higher. Let's just make that a little bit lower. Can you recognize this graph? It should be one that you already know. It starts here on y equals 1, gets back there after 2 pi. Exactly, it's y equals cos x. Wow. So if we differentiate sin x, what we actually get is cos x. All right, that's our first thing that we've learned. What happens if we differentiate cos x? Well, let's have a look. Let's differentiate that one again. I could actually call this the second derivative of sin x, couldn't I? This is basically going to be the first derivative of cos x, and it's also going to be the second derivative of sine x. All right, differentiating this one, where is the gradient 0? Here and here. And this is pi. And up here again at 2 pi. All right, what's the gradient, say, here? Well, it's negative, isn't it? Negative 1. So at pi on 2, we have negative 1. And over here, our gradient would be 1, the same as what it is here. So now we're coming up to this. And it's going between those points smoothly. So again, we have now a curve that's the exact same shape as what we started with, but a little bit different. It's moved along. Now, compare this one with this one. How are they different? And can you describe their difference as a transformation? Well, I can see it in two ways. I can see that if we move this one along pi, then this hump would come along and sit here. So it basically looks like we've slid it along. In fact, this one slid along just pi on 2, and this one slid along even further. So you could think about how to get from one of these graphs to the other by sliding it left or right a certain distance. But I can also describe this one another way. If I compare it to this one, it actually looks like it's just flipped upside down, doesn't it? Instead of the hump going up first, it goes down first, and then not down, but up. So how do you flip something upside down? You take the original formula and you change its y value, not from y, but to negative y. Now, would you write it like this? You could, but probably not. We usually write y equals something. So it makes sense to multiply both sides by negative 1 here and actually write it as that, the negative of sine x. All right, so we've learned a few things here. What we've found is that if we differentiate sine of x, we get cos of x. If we differentiate cos of x, we get minus sine of x. Well, what happens if you differentiate sine of x again? You get cos of x. So if I differentiate this one, the negative out the front comes along for the ride. It's just a constant of minus 1. I'm going to get negative cosx. So the next one down here is going to look like this, with a negative out the front. Now we've got a pattern. Sine x, cos x, minus sine x, minus cos x. What will happen if we differentiate this one? Well, without even looking at the patterns, I'm pretty sure I can do it. If you can differentiate cos x and get minus sine x, then when you differentiate minus cos x, you'll get minus sine x, which is just sine x itself. So then we can actually express a differentiation of y equals sine x or y equals cos x as a phase shift. And what that means is a shift or a translation left or right. Now, we've already seen that when we differentiate sine x, we get cos x. But we also know that cos x is exactly the same as the sine of x plus pi on 2. Now, think about that. If I take the original sine curve, it looks like this, and here's pi on 2 here, then what we're saying is if we shift it to the left pi on 2, this will come across to here, this point will come to here, it'll look like this, won't it? If we shift it to the left pi on 2, and that is, in fact, y equals cos of x. Now, if we differentiate cos of x, what we get is minus sine x, and that is, sure enough, just another pi on 2 across, and etc., etc.